Chapter 3, Exercise 24. Hints. Recall the definition of equivalence relation, definition 2.3. Verify that delta satisfies the axioms of a distance, definition 2.15. Solution. A. If Pn is a Cauchy sequence in X, then it is equivalent to itself. This. Indeed, this. If Pn is equivalent to Qn, then Qn is equivalent to Pn. This follows from the equality here. If Pn is equivalent to Qn and Qn is equivalent to Rn, then Pn is equivalent to Rn. Indeed, the triangle inequality implies this for all n equals 1, 2, 3, and so on. Since this and that, we deduce that limit n to infinity d of Pn Rn equals 0. Let Pq in X star, Pn Pn prime in P, and Qn Qn prime in Q. Since this and that, it follows that, see the solution to exercise 23, the following. So this. Consequently, the quantity here is independent from the choices of sequences, Pn in P, Qn in Q. Let Pn be a Cauchy sequence in X star. For each n, consider a Cauchy sequence here. There exists an integer kn such that this. Consider a sequence here. Given epsilon greater than 0, there exists an integer big N such that this for all n m greater than or equal to big N. Let this. Since this, there exists an integer k0 such that this for all k greater than or equal to k0. If we choose this, then we can estimate as follows. It follows that Qn is a Cauchy sequence. Denote by Q its equivalent class in X star. We will show that Q is a limit of Pn in X star. Let epsilon be greater than 0. There exists an integer big N such that this for n m greater than or equal to big N. Let this and that. Since this, there exists an integer big L such that this for L greater than or equal to big L. Choose the following. Since ml greater than or equal to kn, we have this. Since L greater than or equal to km, we have this. Combining these estimates, we get the following. This proves that this as soon as this. The space X star is complete. D. The equivalent class P contains a constant Cauchy sequence P. By definition of distance delta, we have this. The mapping here, defined by this, is an isometry. Consider big P in X star and let small pn in big P. Given epsilon greater than 0, there exists an integer big N such that this for all little n m bigger than or equal to big N. If little n greater than or equal to big N, then this for all large enough m. It follows that this. We have proved that phi of x is dense in X star. Moreover, we have proved that if Pn in big P, then this. Assume that the space X is complete and let big P in X star. Choose a Cauchy sequence small pn in big P. There exists a limit here in X. Since phi is an isometry, we have the following. On the other hand, from previous considerations, it follows that this. Thus, this and that. Comments. The idea of a presented construction is to identify a Cauchy sequence Pn with a point that should be a limit of Pn. If two Cauchy sequences Pn and Qn are such that this, then their limits must coincide. Any metric space can be isometrically embedded into a complete metric space. If an equivalence relation is defined on a set X, definition 2.3, we can organize a partition of X into a family of subsets A sub alpha in such a way that for any points x, x prime, and x is equivalent to x prime if and only if x and x prime belong to the same set A sub alpha. To do this, it is enough to consider equivalence classes here, and note that either this, a case when x is equivalent to x prime, or this, a case when x is not equivalent to x prime. In this exercise, the space x star is obtained exactly in this way, starting from the space of Cauchy sequences in X with the equivalence relation here. Thanks for watching.